This is when you had two or more equations and you're trying to find the point or points that are true in both equations, that make them both true. So the first method to solving these was to graph them and find their intersection. Now to graph them, we would have to solve for y, and I can already tell I would get kind of an ugly x-intercept, but that's okay. I'm just going to rewrite that and solve for y. Now I could have also found the x and y-intercepts. Sometimes that's easier. I'm noticing here that if I try to find my x and y-intercepts, I'm going to have some weird numbers. So I'm going to take each one and solve for y. And I already see where there's going to be a problem. I hope you do too. Doing this by hand is not exactly the best way to do it, because I'm going to have to estimate where these graphs cross. For my y-intercepts, 11 thirds. Then I'm going to have to go up negative, I can go down -4 and over 5. It's going to be really hard. But I can use the calculator. So this one is not actually the best one for graphing. I'm wishing I'd put another example for graphing. But it's a good one to show that graphing is not always the easiest. Now, if you do have a calculator, it is. So what I could do is plot each graph. And the other one is 2/5 x plus 1/5. I'm going to press graph. And I can see where they cross. So I can tell that one of them's doing something like this. One of them's doing something like this. But it's hard to tell exactly where they're crossing. I can guess, but that's not good. So in the calculator, if you press second trace, there's an option for intercept. And it asks you if this is the first line. Yes. Is this your second line? It's a second curve. Yes. Do you feel like guessing? Now that comes into play if we had more than one spot. But right now there's only one place, and it says the intersection is 2, 1. So graphically, if you have the technology, it will always work, but you have to always solve for y before you can put it in the calculator. Now, thinking about it graphically, there's 3 cases that we can have. We can have what happened here, where we have 2 non-parallel lines and they cross at one point. But we could also have 2 parallel lines that never, ever, ever cross. That would be no solution. Now the third option, and this does happen, is what they call coincident lines. That means if I graph the first one, it graphs like this, and when I graph the next one, it actually graphs right on top. And we end up with infinite solutions, meaning every point is the same on both lines because they are basically the same line. So graphing, not always the best method if you're doing it by hand. Substitution is one of the methods that we learned back in Algebra 1, Algebra 2, that we're going to review here. The substitution method can also get a little bit ugly sometimes, but the first step is to solve one of the equations. Solve one equation, solve for one variable. We want to take one of the equations and get one of the variables all by its little lonesome. Well, second equation looks good for that. I can get x by itself real fast. Now, step 2 is to substitute into the other equation. So I'm going to be taking this expression for x, and it's going into the other equation for x. So I end up getting 2 parentheses 2y plus 3 plus 3y equals 4. And now I only have one variable. Remember, these are on the same side, so they just combine. And then we subtract the 6. And we found y. Now we don't want to just find y because we need a point. So now we need to go back and find x. I can plug this y back into any of these 3 equations I want. I like the first one. Well, the rewritten first one. Now, if you do have a graphing calculator, showing tips today, you can do 2 parentheses, alpha y equals, gives you a fraction, negative 2 over 7, parentheses, plus 3, and it actually gives you back a fraction answer, which is wonderful because we prefer fractions to decimals any day of the week. Well, unless we're dealing with money, but we'll get into that later. And then we're going to write our solution as a point. Okay. One more where we're going to do substitution. Now, which one would it be easier to isolate a variable on? The first one would get kind of ugly because it's got a 4 and a 5. I think the second one would actually be easier. So I'm going to take that second equation and solve for x because I see that 9 is divisible by 3 and 12 is divisible by 3. So that would be a good one. So step 1, I'm going to take that equation and solve for x. Now, I need to take that and substitute into the other equation. We end up getting a nice answer for y. Now, I also need the x, so I'm just going to plug right back into this one. Whoops. And I get that x is 2. So our solution is 2, 2. Now, this one's an easy method, but sometimes not too practical. Think back on that first example. No matter how I rewrote it, it was still just going to come out ugly. fractions everywhere, it wouldn't have been good for substitution. So now we introduce the elimination method. The elimination method is where we want to eliminate a variable. So we have to choose somebody to vote off the island. It can either be X or Y. But the way we get rid of it is we add the two equations so that one variable disappears. Now there's several ways we can do it. I could make this be a 2x and this be a negative 2x. I could do a negative 10y and a positive 10y, but that would mean bigger numbers. So I think I'm going to get rid of x. So step one is we're going to rewrite it to get rid of one of the variables. So I'm going to leave the first one like it is, but this second equation, I'm going to multiply the whole thing, both sides, by a negative 2. So I'm going to do negative 2. So negative 2 times x is negative 2x. Negative 2 times 2y is negative 4y. Then negative 2 times 3 is negative 6. When I add these two equations together, the x's are going to go away. And I get negative 9y equals negative 2. So y is 2/9. Quick. Now all I have to do is plug it back in to find the other one. And it doesn't matter which equation I pick. I think I'm going to go with the second one. X plus 2 times 2/9 equals 3. Give you a trick here. X equals 3 minus 2 times 2/9. And then I can just use the calculator. So if you're bad with fractions, rely on your calculator to help you out here. And you don't even have to close the parentheses. It'll do it for you. Notice that sometimes we get good answers, sometimes we get ugly answers, and that's okay. It happens. All right, so the next one, let's see. Since that's twice as big, if I multiply that top equation by like a negative 2, that would work. So step one, I'm going to get negative 8x minus 6y equals negative 8, and leave the bottom one just like it is. But something weird happens on this one. When I add these together, I end up with 0 equals 10. All the variables disappeared. That means it's one of those two special cases. And the way I decide which case it is the statement I'm left with true or false? Well, this is false. 0 does not equal 10. So that means there is no solution. The next one's very similar. I have a 4 and an 8, so I'm going to multiply the top one by a negative 2. I don't know why all the examples I'm having to multiply by the same thing. It's weird. And a 4. The bottom equation. Oh, bottom equation is exactly the same but different signs. What that tells me is that they are the same equation. So this is really infinite solutions. Now let's see how we can apply some of these. Okay, a person has $200,000 invested, part at 9%. This looks similar to a problem we did in one of the earlier sections. And part at 8%. If the total yearly income from the two investments is 17,200. How much is invested at 9% and how much at 8%? So let's label the 9% as X and Y as 8%. So if I took the amount at 9% plus the amount at 8%, I'd get the full 200,000. Now the next part talks about the income from those investments. So I'm getting 9% of that value. So 0.09 of X plus 8% of Y is going to be the amount I'm getting out of the investment. So 17,200. Notice the big numbers. I wouldn't want to graph this. A lot easier to solve. And this is actually a lot easier to do our substitution and our elimination method. But I'm going to do something kind of interesting here. So I'm going to multiply the top one by like a negative 0.08. Okay, so by negative 0.08. All right, so the first one would be negative 0.08x, negative 0.08y equals times 0.08 gives me negative 16,000. Now let's bring the other one over. And I didn't do anything to him, so he just comes over just like he is. When I add these two equations together, y will disappear. Now, negative 0.08 plus 0.09 is going to give me 0.01x equals, and I'll get 1,200 on this side. And now I'll take 1,200 divided by 0.01, and I get x is 120,000. So that means we're going to invest $120,000. This was X, so that's at 9%. And how much would be left? We had 200,000, so there's going to be $80,000 left to invest at 8%. A nurse has two solutions which contain different concentrations of a certain medication. One is a 12.5% concentration and the other is a 5% concentration. How many cubic centimeters of each should she mix to obtain 20 cubic centimeters of 8% concentration? So if I make, let me make this one X and this one be Y. Okay. The total amount is 20 cubic centimeters. The percentages is a little bit of a different story. So 12.5% would be 0.125 of this concentration. The other one is 0.05 of medication Y, and we want that to equal 0.08 of the 20. Oh, of the total. Okay. So I need to clean that up a little bit. What is 0.08? That's 1.6. Okay, so I'm going to leave that bottom equation just like it is. 0.125x plus 0.05y equals 1.6. Okay, the top one I'm going to multiply by something. Let's think, what should we multiply by? How about negative 0.05? Okay, so I have negative 0.05x, negative 0.05y equals -1. Ooh, that was nice. Okay. 0.125 minus 0.05 is really what we're doing. We get 0.075. These are going to cancel. Over here, I'm just going to get a 0.6. And when I solve, I get 8 for that one. So that means we need 8 cubic centimeters of 12.5 solution or concentration. And how much of the other one? 12 cubic centimeters of 5%. Notice it's going to take more of the 5% if we want the overall concentration to be at an 8. We're trying to combine 12.5 and 5 to get that 8. All right. Using the U.S. Bureau of Labor Statistics data for selected years from 1950 projected to 2050, the number of men and women in the workforce is modeled by these two equations, where T is the number of years past 1940. Graphically find the years these functions predict that there will be equal number of men and women in the U.S. workforce. So this one is definitely a calculator one. And we're trying to find where those two meet, where the number of men and the number of women meet. So 0.591, we'll use X in the calculator. It's not as acquainted with T. And I'm going to go to my graph. Let's see. What's the problem here? Why am I not seeing it right now? Because it's too tall, right? So maybe I need to zoom out. And one thing you can do is do a zoom out. Press the 3 and press enter. Let's see if that helped any. Notice I still don't see where they cross. So we may have to play with the window a little bit. Let's make this go all the way to 100 and go to 100. Let's see if that helps. Here's the first one. Oh, we're almost there. They're crossing right there, so I'm going to keep doing that. Let's just go to 200. Here's the first one. Here's the second one. Do we see where they cross? We do. So remember, we're going to do second calc, intersect, enter, enter. Guess, I don't really need to. It gives me the intersection. Now, what does this mean as far as our values? So the X is like our T, that's our time. So 100, so let's write it down. It's 124.1, comma, 110.6. We'll just go there. This is the number of years past 1940. Ooh, so if I took 1940 plus 124, so this would be at the end of the year 2064. Wow. It's actually going to be the beginning, because it's right past 124. The beginning of 2065. There will be 110.6 million each men and women.